Now we are ready to understand Newton's second law of motion. So let us take an example once again. Let us say a cyclist right now is at point A and he wants to reach point B. Let us see how much time will this bicycle take to reach from point A to point B. Let us start its motion. Now if you see in the clock, it takes 5 seconds to reach from point A to point B. Now in order to move from point A to point B, we know the cyclist would have actually applied certain amount of force, right? So here the force was a particular value. Now we change the scenario. Instead of this bicycle, we have a car right now. Now think about this. Would the force applied by car be the same or different? Will be less or more? And you guessed it right, obviously the force applied by the car would be more. So what about the time taken? Would the time taken be more or less? And obviously the time taken for the car to travel from point A to point B would be less. And you can see in the time, we can see that the time taken is just 1 second. That means when the force is more, remember, when the force is more, time taken is less. That means the change in velocity is very, very fast, right? That means the rate of change of velocity is fast. But we know that velocity and momentum are related. More the velocity, more the momentum. That means more the force, more the change in momentum, or we can say more quicker is the change in momentum. So what do we conclude from this? More force, faster is the change in momentum, or quicker is the change in momentum. Now faster means it is related to time. So in physics, time can be understood by the word rate. So we say rate of change of momentum. That means force is directly proportional to the rate of change of momentum. We know what directly proportional means, right? If one physical quantity increases, the other also increases. So now this is nothing but the statement of Newton's second law of motion, which says that the rate of change of momentum is directly proportional to the applied force. This is the first half of the statement. I'll repeat it once again. The rate of change of momentum is directly proportional to the applied force. Let us see the statement. The rate of change of momentum is proportional to the applied force, right? And the change of momentum occurs in the direction of the force. The direction in which we apply the force, obviously the change in momentum will be in that particular direction. So here we have rate of change of momentum and here we have force. So these are the two important components of Newton's second law of motion. Now, from Newton's second law of motion, what we can do is we can derive the formula for force, which is also called as the equation for Newton's second law. Remember, the formula for force is nothing but the equation or the equation for Newton's second law of motion. Let us see how to derive equation for Newton's second law of motion. So here we have this car. Now this car will have certain amount of mass to it denoted by small letter m. And since this is its initial position, this particular car will have certain amount of velocity, which will be initial velocity. But we know for a fact that mass and velocity is nothing but the momentum. Now since this momentum is the initial momentum, we will write this momentum as P1. So this P1, that is momentum, is nothing but mass into velocity. So this will be mass into initial velocity. So P1 is m into u. Very simple, right? Now, in order to move this car, we need to apply certain amount of force denoted by capital F for time t, right? So it will start moving and we know the mass would not change. Mass would remain as it is. But the velocity will now become final velocity denoted by small letter v, right? So initial momentum was denoted by P1. So final momentum will be denoted by P2. And P2 will be m into v. So we have the value of P1 and P2. So how do we use these two values? Now we have to use the statement for Newton's second law of motion. It says that rate of change of momentum is directly proportional to the applied force, which simply means that force is directly proportional to the rate of change of momentum. Now force is denoted by capital F. So we write capital F. Alpha remains as it is. Now rate of change of momentum. Now we know change of momentum can be found by subtracting the final momentum with the initial momentum. So we have P2 minus P1 because P2 is final momentum and P1 is initial momentum. And rate, we know that rate means divide by time, so we have upon time, right? So we have F is equal to P2 minus P1 upon small t. Now, do we have values of P2 and P1? We do have them, right? This is P2 and this is P1. So what is P2? P2 is mv, so we write mv minus mu upon t, right? So F alpha remains as it is. Now can you see something common in the numerator? We can see m is common, so we take m common and in bracket we have v minus u and upon t remains as it is. Now think about this. We have a formula v minus u upon t. Now that particular formula is the formula for acceleration, right? And acceleration is denoted by small letter a. So F and alpha remains as it is, m remains as it is, but v minus u upon t becomes a, that is acceleration. So we have F alpha ma right now. Now we know that we cannot use the proportionality sign. We have to remove the proportionality sign and put an is equal to sign over there. But to remove the proportionality sign, we have to add a constant of proportionality. So here what we'll do is, we'll insert a constant of proportionality that is nothing but k. So we get k into m into a. Now we'll put the value of k as 1. So the constant of proportionality k will be 1, right? So if k is 1, we know that 1 into m into a will give us m into a. So this F is equal to ma is nothing but the formula of force as well as the equation of Newton's second law of motion.